All right, I had a student ask me about a related rates problem where we have more than one variable in the problem and they're both or all changing with respect to time. So let's look at an example. So imagine we have a cylinder like so. You'll see why I'm not an art teacher. There's my cylinder, and the cylinder has a radius and it has a height. And what we're going to imagine is that for some reason, the cylinder's radius is changing and the cylinder's height is changing as well. And what the question asks us to determine is how fast is the surface area of the cylinder changing. So let's write an equation for surface area. The surface area of a cylinder is the circle on top, the circle on bottom, and then the curved surface along the middle. So you have a circle on top and a circle on bottom. And then if you unwrapped that middle chunk, you would have a rectangle. And the rectangle is 2 pi r wide because that's the circumference of a circle, and it is h tall. So if I think of every one of those as a function of time, then I can take the derivative with respect to t. So the derivative of the surface area changes over time. And then here, I'm going to use the power rule. 2 pi is just a constant, so I can use the power rule, multiply it by 2, 4 pi r. But then remember that the letter r is not just a variable by itself, it is actually secretly a function of time. So I just did a function inside of a function. When I'm doing a derivative of a function inside of a function, I use the chain rule. So the chain rule says you multiply by the derivative of the inside function. The derivative of the inside function is dr dt. Same sort of idea on the second piece. I'm going to use the product rule, however. So the derivative of the first piece is 2 pi, because that would be if r was an independent variable, but it's actually a function of time. So 2 pi dr dt, that is the first part of the product rule. That's f prime, then times g, plus f, 2 pi r, times g prime, dh dt. And so that is the total change of the surface area. And you can see that in order to know the change of the surface area, I need to know the radius, the change in radius, the height, and the change in height. And that kind of makes sense. Okay, so I was told that the radius is decreasing at a rate of 3 centimeters per second, and the height is increasing at twice the rate of the radius. So the radius is decreasing. That's why it is a negative symbol. And the rate of change of the height is increasing. So it's 2 times dr dt, but dr dt was negative, so I'm going to put a negative in front to make it into a positive. In other words, it's 6. So that means that the change in my surface area, at this point, I'm just going to plug it all in and see what pops out. So 4 pi. I need to state what the r and the h values are as well. And the question gave us those values. It said the height was 10 and the radius was 12. Okay, so the height was 10, the radius was 12. And I want to mention something here. Notice that I did not plug those in to the original equation. I saved them until I took the derivative. You want to take the derivative of the equation that has letters in it. Otherwise, you're going to get lots of zeros because you're taking the derivative of things with numbers. Okay, so anyway, what am I doing? I'm going back to here, and I'm just plugging in all the values that I've written down. 4 pi r is 12, dr dt is negative 3, plus 2 pi dr dt, negative 3. H is 10, plus 2 pi r is 12, dh dt is 6, and whatever that comes out to be is the answer. Um, uh, there's a chance I make a mistake here with my mental math. I'm going to factor out a pi. Let's see. That is 4 times 12 is 48. 48 times 3 is 154. And it's a negative. 2 times 3 is 60 times 10. 2 times 3 is 6 times 10 is 60. And then 2 times 12 is 24. 24 times 6 is 120 plus 144. So I guess that becomes like negative 70 pi. And now whatever units make sense here. I was told my original measurements in uh, centimeters per second. And I want you to notice if you look back at the units in my surface area formula here, I had radius, well, that's centimeters, and then this is centimeters per second. At every part of the related rates problem, you'll notice that I had a unit of centimeters times a unit of centimeters per second. And so my final measurement is square centimeters per second, which is great news because we're talking about surface area. That's always good to go back and double check that the units make sense. That might help you remember to do things like the product rule or to do the chain rule where you multiply by dr dt, because doing that makes your units land on the appropriate values. All right, thanks for watching. Let me know if there's anything I can do to help.